first one up is Wenshen Song, and he's going to give a presentation on the multitask deep learning framework for sales forecasting and product recommendation.
All right, thanks for the introduction. Hello, everyone. My name is Wenshen Song, a data scientist from Pros Company, Houston, Texas. Today, I will introduce our work named Multitask Deep Learning Framework for Sales Forecasting and Product Recommendation. So this work is done by the Pricing and Sales Intelligence team at Pros. Many thanks to Yan, Farouk, and Justin for collaboration. First, we will introduce the motivation of this research, which includes two parts, forecasting and recommendation. So why we need sales forecasting in business? Because they help overall business planning, budgeting, and risk management. In a word, forecasting can help companies to make better business decisions. On the other hand, why is recommendation so important? From business analysis data, we can see that customers contribute more revenues when buying multiple products, but it is not easy for the sales representatives to find those opportunities. So, if we can find the purchase pattern and recommend products for those purchase gaps, that will definitely help to create more revenues. We have already introduced the forecasting and recommendation in business. So, is there any connection between them? Can we borrow the experience from solving one problem to help another? What are the challenges of solving these problems? In the following slides, we'll take transaction data as an example to illustrate those problems. In business scenarios such as B2B or e-commerce, there are plenty of transactions and can generate large volume of transaction data. For a given combination of customer and product, all the involved transaction records should form a time series, with x-axis as the time and y-axis as the target values, such as price, revenue, or ratings, depending on different business scenarios. And we want to forecast the time series. Because for transaction data, we have more than one customer and product, and we need to forecast each of them. So the first challenge in transaction data is forecasting at a granular level for each customer and product combination. If we spread out those time series into customer product metrics, we can find it is very sparse with a lot of gaps. So how can we find those gaps based on the existing purchase patterns? Here comes the second challenge, recommendation for the gap. As a result, for transaction data, we want to perform both forecasting and recommendation based on different feedback of the data. But how to do that? The most straightforward answer is using different single task models. However, those independent models have no interactions with each other. On the other hand, if we can build a multitask model, can integrate different feedbacks and perform joint learning, it will play an important role in different industries, such as e-commerce, B2B, or airlines. As long as there are transaction data consisted of customer, product, and time. Let's take a look at some details about the multitask model. As introduced in previous slides, transaction data are consisted of time, product, and customer. For the input, the product ID and customer ID, along with their features, will be embedded and concatenated. But for time ID, we will use Fourier filtering to convert them into different orders of sine and cosine wave, and then concatenate with the embedding vectors. So this step will help to fit the time series with those like Fourier bases and extract the seasonality. The obtained long concatenated embedding vector is a good representation of the original input. For the next step, the obtained embedding vector will be fed into two independent deep neural networks. So the first one is for forecasting, and it will fit and predict the y values. Here we use the example of revenue, and we call it prediction task. And the second one will deviate the recommendation and fit the purchase probability. And we call them recommendation tasks. And finally, we will combine those two objectives together using a weighted sum. Therefore, the loss function of these two tasks will try to drop at the same time and compensate for each other. And the concatenated embedding vectors shared by these two tasks will preserve the connection between them. As a result, both deep neural network will work jointly to obtain an ideal embedding for both prediction and recommendation, as well as good accuracy for each individual task. Although the prediction and recommendation task use the same input data, it doesn't necessarily mean that they will utilize the same kind of feedbacks. So, for example, here we have a sparse customer and product matrix. The blue squares, which are revenues, positive transactions happen in real world, providing the so-called explicit feedback to predict the revenue. However, the missing transactions or gaps in light gray squares never happen in real time. We call them negative transactions, and they can still help to reflect the preference of a customer. If you don't buy something, probably you just don't like it. To effectively utilize negative transactions, we need to sample them due to the data sparsity. And those sampled negative transactions, along with all the positive transactions, will be fitting to the recommendation tasks to fit the purchase probability as implicit feedback. Based on different feedbacks, we need different metrics for those two tasks. For prediction, we want to make sure we're predicting the right y values, such as revenue or price. And we can use the classic mean squared error, MSE, or mean absolute percentage error, MAPE, as our metrics. But for recommendation, we're predicting the purchase probability for gaps. But eventually, we want to know if our recommendation is good or not. So we will rank the purchase probability of different products for each customer. Then we select the top K as our recommendation to see if they match the real products. We will use the record K to measure this kind of relevance. Besides, we have this diversity at K to measure the exposure of each product in our recommendation. So a small diversity means the model will recommend the same products again and again, even for different customers, and vice versa. Here are some results of real-world transaction data from manufacturing industries. We have 3 million transactions with about 4,000 products and 2,000 customers, and the time range is about 2 years. And we compare the results of multitask model with other single task models. For prediction task, our reference a moving average predictor and the last revenue predictor, which just predict a flat line using the last revenue of history, as shown by this green line. So we can clearly see that the multitask model have a better MAPE value than both of them, if the customer product combinations are not brand new in the test. If they are, the moving average and last revenue predictor cannot even forecast due to the lack of history. But our multitask model can still do that. For recommendation task, we have this alternating least square ALS, explicit recommender and implicit recommender as reference. Due to the implicit essence of recommendation, we can see that the implicit recommender can do a much better job than explicit recommender. But the multitask model still have a better recall and overwhelming diversity. The reason is that the LRS implicit recommender is a global method, performing matrix factorization on all the positive and negative transactions. Meanwhile, in multitask model, we have negative sampling, so the prediction of purchase probability is not so restricted like the LRS, therefore lead to a much higher diversity. Those results indicate that our multitask model can improve both prediction and recommendation tasks simultaneously by combining the learning experience from each individual tasks together. Here is the conclusion. The multitask model has successfully combined explicit and implicit feedbacks for multitask objective, and it can generate comparable or even better performance compared to the single task model due to the joint learning. And also, it is a general solution because it is applicable for any transaction data that have customer, product, and time structure. Thank you, and I'm looking forward to any questions.
Hi, thank you for your presentation, Wenshen.
Thank you.
We